Hello everyone, my name is Haidegger and I will now present my master thesis, Evolutionary and Gradient-Based Optimization Methods in Tensor LEED. First to the basics, LEED or low energy electron diffraction is a commonly used method for surface structure characterization. However, it's not possible to precisely determine the surface structure with LEED. For this, LEED IV is necessary. In LEED IV, the intensity of the diffracted electrons is measured over the incident electron energy. With this measurement, we get these experimental curves, and the theoretical curves, the blue ones, can be calculated with a set of input parameters. The R factor, which you can see on the left upper corner, is one scalar value, which tells how close the theoretical curve is to the experimental one. The smaller the R factor, the more similar these two spectra are. In the calculation, it looks more like this. So we have, on the left is our parameter vector, which is basically the displacement, the vibrations of the atoms, and the occupation of the elements. Then we calculate the intensity, and from this we calculate the R factor. It's important to understand that we want a theoretical curve with a small R factor, because this means we have the right parameters. However, it's not easy to find this, since a small change in the input parameters leads to a big change in the spectrum. The algorithm basically just sees our input vector. This is a normalized vector, so all the parameters are from 0 to 1. And our output, which is the R factor, what we want to minimize. This way, all the parameters are treated equally, and we get the R factor as the output. This is called a black box optimization. So, to understand why we use the algorithm that we use, it's important to understand the R factor surface. So what we can see here is, on the left side, we already minimized almost all of the parameters except these two. And what you can see here is the range of the R factor is quite large, and we can definitely identify a global minimum in the middle. However, if the parameters are not minimized, we cannot identify a global minimum, and the range of the R factor is very small. So it's very hard to find this global minimum, or better, the global minimum basin, but then it's easy to find the minimum. This is the reason why we split the algorithm into two parts, first the global search and then the local search. In the global search, we try to find the global minimum basin, which is the basin containing the global minimum, and in the local search, we further refine the R factor to find the actual global minimum. For the global search, we used the evolutionary algorithm, and for the local search, we used a gradient-based algorithm. This new algorithm we compared with an old one, or with a previous one, and we compared it for hematite and for the first structure optimization. The previous algorithm was performed on a CPU and took around 7.5 hours. And the new one is written for a GPU, so it was also performed on a GPU and took around 14 minutes, which is a good improvement. That's everything from my side, and I want to thank every one of you for your attention.